Welcome to AQA Spectroscopy Lesson 3C, which is Proton NMR. If you need to look at the textbook, then it's pages 146 to 152. This is the last of the 3 videos on NMR spectra. If you haven't watched the previous 2, then you should go and watch them now before watching this video. So lesson objectives for this lesson are to know the use of the delta scale for recording chemical shift, understand the chemical shift depends on the molecular environment, understand how integrated spectra indicate the relative numbers of proton atoms in different environments, and be able to use the n+1 rule to deduce the spin-spin splitting patterns of adjacent non-equivalent protons limited to doublet, triplet and quartet formation in simple aliphatic compounds, so we don't need to worry about aromatic compounds. So in proton NMR, just like carbon NMR, the number of peaks in the spectra is equal to the number of hydrogens in chemically different environments, and just like last time I've underlined that because it's really important, chemically different. So you can have 2 in the same molecule which are in identical chemical environments, you'd only get 1 peak. So once again I'm going to ask you to predict the number of different environments and therefore the number of peaks. So I'll talk you through 2 examples first. So this first example here is similar to the one we had before. So you've got 1, 2, 3, 4 different hydrogens in different environments, and this OH here and this OH here are different because this one is a carboxylic acid, so it's next to the carbonyl group. For butene, just like we saw on the carbon NMR, then we have some equivalence going on because the molecule is symmetrical. So these end carbons are exactly the same as each other, they're in an identical chemical environment, so you only get 1 signal for those. And these 2 alkene carbons in the middle are also identical. So overall you get 2 signals, 1 for this one on the left and 1 for the next one. So just like in the last video, I'm going to talk you through the steps. And step 1 is to predict the number of different environments and therefore the number of peaks, just like we did with carbon. So the only difference is that we're looking at hydrogens rather than carbons. So if you look at this first molecule here, which is 3-hydroxypropanoic acid, you've got 1, 2, 3, 4 different hydrogens. And although you've got 2 OHs, these OHs are in different environments. This one here on the right, the OH, is next to the carboxylic acid, and therefore it's in a different environment than this one, which is just next to a CH2. So you would see 4 signals in the proton NMR spectra. Now butene is like our previous example. We looked at it on the carbon NMR video, and here we've got 1, 2, 3, 4 hydrogens. However, just like last time, there's a plane of symmetry here, which means that these 2 inner hydrogens are actually in the same environment, and therefore you only get 1 peak. And these 2 outer hydrogens are also in the same environment, and therefore you only get 1 peak for them. So you get 2 peaks in total. So this is what the actual spectra look like. So you've got 4 peaks, you've got 1, 2, 3, 4 peaks for that one, and for butene you've got 1, 2. Don't worry about the fact that these peaks aren't individual single peaks, we'll talk about that later. So this is what the spectra actually look like. So you can see 3-hydroxypropanoic acid, you've got 1, 2, 3, 4 peaks, and for butene you've got 1, 2. Don't worry too much about the fact that these peaks that aren't on the bottom one aren't single peaks, we'll talk about that later. So what I want you to do now that I've shown you those 2 examples, is pause the video and see if you can predict the number of proton environments in each of these examples. So hopefully you managed to work that out. This is the same example, this top one here is the same example of butane that we had on the carbon NMR video, because we've got 1 hydrogen here, 1 there, 1 there, 1 there, but so we've got 4 hydrogens, but these end 2 are equivalent and these middle 2 are equivalent. So on our second example here, we've got 4 different hydrogens because we've got 1, 2, 3, 4. Because we've got this OH on there, on the right hand side, it's not symmetrical, so they're all in different environments. You've got 4 different signals. Benzene, we looked at in the carbon, and it's important for this, ignore the double and single bonds in the ring here, because all of those carbons are equivalent, because benzene actually isn't like that. It's a more complicated acid or more simple structure, depending on which way you look at it. So don't worry about the double and single bonds. So because you're not worrying about double and single bonds, all of these hydrogens are now equivalent, and therefore you only get one signal. However, on this right hand side one, you've got an OH group there and you've got a CH3 group there. So what that means is that this hydrogen here on the OH it gives you one peak, and then you've got one peak for these two next to it, and then you've got one peak for these two next to the CH3, and then one for the CH3. So you've got 1, 2, 3, 4 different environments. So let's go now to step 2, which is to predict each proton's chemical shift. And this is a table very similar to the one we had on the carbon. So you've got your molecule there, which is colour coded. So you've got your one in green, which is that OH. Now we've got a similar scale on the bottom here that we had for the carbon, except the values are different. You can see the values are much smaller. They only go up to 12 on the left hand side, whereas we went up to about 200 on the other one. So we're looking for an OH, and if we look for an OH, then we find it here, which is basically almost anywhere on the spectra. So it can be anywhere from 1 to 12. So on that green, we're just going to put 1 to 12 there. For the hydrogen labelled 2 with the orange, that's a CH2 next to an OH, so it's an OCH. So that's going to be somewhere here, which is about 3 to 4.5. So that's where we'd expect to see that one. For the hydrogen labelled 3, that's a CH2 next to a carbonyl. So we'd expect to see that here, that's on this bit here, we've got a C double bond O next to a CH, so that's going to be round about 2 or 3. And for number 4, that's an OH of a carboxylic acid, so that's going to be all the way over here on the left, round about 11 to 12. So this is the actual spectra that you can see. We've got 1, 2, 3 peaks, just as we predicted, and if you go and look back at the table, you can see that they're roughly where we said they were going to be. Now a quick word about integration of NMR spectra. You can't do this with carbon NMR spectra, but with proton NMR spectra you can tell by the integration how many hydrogens give rise to that particular signal. So if the bigger the area under a peak means that the more hydrogens that give rise to that peak. So you can look at the ratio of the areas under each of the peaks, and that will tell you the ratio of the hydrogens. So you can see whether you've got a CH, a CH2, a CH3, or if you might have a ratio of 6 to 1 because you've got 2 CH3 groups which are chemically equivalent, in which case you'd have 6 hydrogens. So now we come to one of the differences between proton NMR and carbon-13 NMR. Before we talked about integration, which was one of the differences, but the other difference is spin-spin coupling. And you don't see this on carbon NMR, but you do on proton NMRs. So on high resolution proton NMR, then you see, rather than seeing a single peak, you see little clusters. And these clusters can help you identify the number of protons in the environment next to it. So they can give you a lot of information about the structure of the molecule. Now all you need to remember for this is the n+1 rule, and there is a lot of theory behind this, so you can look up the theory if you want to, but you don't need to know it. All you need to know is that if n is 0, then n+1 is 1, so you see a singlet, which means you see a single peak. If n is 1, then you see 1 plus 1 is 2, which gives you a doublet, so you see a peak, which is 2 peaks. Instead of seeing 1 peak, you see 2 equal height peaks. If n is 2, then it's 2 plus 1 equals 3, so you see a triplet, which is 3 peaks. Now in this case, you have the middle of the 3 peaks will be twice as high as the 2 outside peaks. And you don't have to worry about why this happens, but you can look it up if you're interested. If n is 3, then you get a quartet, which is good because 3 plus 1 is 4, so you get a quartet. And that's, again, it's not 1 to 1, you get the 2 peaks in the middle are equal height, they're a ratio of 3, and then the 2 outside ones are a ratio of 1. And the gap between the peaks, each of these peaks stays the same, and it is determined by the adjacent proton environment. and that's called the coupling constant, which you don't need to worry about at A level, but it is very useful as you get into NMR. This little Pascal's triangle here on the left, you don't have to worry about, but it is a way of remembering the heights, because if you look at the top when you've just got one peak, then you've got, that tells you the relative height. Obviously there's no relativeness because there's only one peak. Then if you get down to the second line, it's a doublet, so it's 1 to 1, so that's the height of the peak is 1 to 1. Then if you've got a triplet, it's 1 to 1, so it's 1 and then 2 and then 1, and then 1, 3, 3 and 1. So we just need to worry about the top 4 rows of that. So we can use the n+1 rule to identify how many protons are in the environment next to it. And I think on the previous slide I forgot to say what n was. So n is the number of adjacent hydrogens, so it's the number of hydrogens on the carbon next to the carbon that the proton you are looking at is on. So in this molecule here that we've got, this is the spectra underneath that we can see, and you can see there we've got a triplet, which you can quite clearly see is the middle peak is twice as high, so it's a 1 to 1. So there's a triplet, there's a singlet, and there's a quartet. So if we look at this molecule, we can see why we've got that pattern. We'll start with the right hand side of the molecule. If you look at this right hand side of the molecule, that's a CH3 group, and the carbon next to it hasn't got any hydrogens on it. So because there's no hydrogens on the carbon next to it, n equals 0. So if n equals 0, then you only see one peak, because n plus 1, 0 plus 1 is 1, so you only see one peak. So this far right carbon, the CH3 group, is this peak here, which is a singlet. Now if we go to the far left of the molecule, you've got another CH3 group. However, this CH3 group is next to a CH2, so there's 2 hydrogens on the carbon next to it, so n equals 2, so that means n plus 1, 2 plus 1 is 3, so this one CH3 group on the far left is going to be a triplet, so it's going to be this one here on the far right. Now that leaves us with this CH2 group here, and that is next to a carbon which hasn't got any hydrogens on, but it's also next to one that's got 3 on, so n plus 1, 3 plus 1 is 4, so you'll see a quartet, which is why we see 4 peaks here. And going back to the integration, which I briefly talked about but wasn't on the slide, so these two CH3s here will have the same area under the peak. So this, if you've got the integration trace for this molecule, this singlet here would have the same area underneath it as this triplet here, because they're both equivalent to 3 hydrogens. Whereas this one here is a CH2, so this quartet here would have an area a relative area underneath it of 2. So here we get to our last slide, which is just the lesson objectives again. And all I want you to do for this is just read over these and make sure you understand them. If not, rewatch the video or go and have a look at the textbook or some of our online resources to make sure you understand it.